start.
Okay, so thanks for the opportunity to speak here. Subeom Kang in Sungyeon University. This talk is based on a work to appear with Professor Won-il Bak in Jeonbuk National University and Dong Han-hyun in Busan National University. Right. Okay, so in this project, we solved the Hilbert equation numerically, and we are going to compare the result with the well-known analytic result, which is called the Hartle-Hawking wave function. We compare both the result and the slow limit and the non-slow limit. Before doing that, so I'm going to briefly explain the concept of Hilbert equation and what kind of boundary condition we used and what kind of model we used. Okay, so we start with a simple action. This is a simple model, gravity with a single scalar field. R is the rich scalar. Our metric such is given like this. Okay, so we assume the spherical symmetric metric. This is A is scale factor and N is a rest function. We assume homogeneous field of phi, and after integrating the spatial part, we obtain this form of action. So we obtain the Lagrangian below. So now we have Lagrangian, then we can define the canonical momentums. So we can do the Legendre transformation to get Hamiltonian. So pairing Lagrangian by the rest function n, we obtain the Hamiltonian constraint. Yeah, the right side, h psi 0, is the quantum version of Hamiltonian constraint. The Hilbert equation is just nothing but the Hamiltonian constraint in the wave function form. We just exchange the canonical momentum to differential operators, and then the Hamiltonian constraint leads to this wave equations. The alpha is log A. The interpretation of the psi is that the probability we find a universe with size alpha with field value pi. So the Hilbert equation is actually a hyperbolic differential equation. In general, to solve the hyperbolic differential equations, we need 4 boundary conditions. The first 2 boundary conditions is the boundary conditions at initial alpha I, at initial scale factor, which means the green bar. And the another 2 are the boundary conditions at the initial field value pi I and the final field value of phi f. So here we assume subhorizon scale initial conditions. So the initial scale factor is much smaller than the horizon scale. For the first boundary condition, we just use the Hartle-Hawking wave function, which describes no boundary universe. So the wave function is the Hawking-Hartle wave function in the subhorizon limit. So because we have this analytic form, we have we have the both boundary conditions at green bar, even the differentiation. But when it comes to boundary conditions at pi I and pi f, actually we don't have any special motifs like Hartle-Hawking wave function we used. So, but one of the simplest way to impose the boundary conditions at pi I and pi f, we just simply chose the boundary conditions as periodic boundary conditions. The advantage is that if we just impose the periodic boundary conditions like that, so we don't need to specify those functions at the 2 boundary. Okay. So this is our model. This is a simple periodic potential model we can think of. So yeah, V0 and M are constant, and delta is the periodicity in the field space. So so the potential has local maximums at pi equals 0 and local minimums at pi equal plus minus delta. Okay, so first let's start with the slow roll limit case. Okay, this is our numerical result. So we chose this parameter V0 and delta to satisfy the slow roll condition, and we chose R pi to satisfy our some initial assumptions of sub-horizon scale. First, note that the dominant peak appears near R pi equals 0, 1. You see the dominant peak there, which corresponds to the horizon in the given parameter set. In the sub-horizon scale, there, you see some exponentially increasing curve. And in the super-horizon scale, you see the decreasing oscillating patterns. So note that no changes along pi direction. So yeah. To compare to our numerical result to the analytical result, okay, so let me see how we solve the, how they obtain the analytic solution. Actually, the analytic solution is obtained through the following process. In the pi is pi 0 constant limit, the Wheeler equation reduces to like this simple equations. Psi prime A plus B effective consternation A. But this is just the potential work problem in quantum mechanics, like the left figure. It's very similar to the alpha decay in nuclear physics. When the wave turns the potential, it exponentially increases and then re-oscillate after the tunneling. Yeah, this is the known analytic result. Yeah, this is Hawking-Hartle wave function in the sub-horizon limit and in the super-horizon limit. Note the same tendencies in the both numerical and analytic solutions. You see the peak positions exponentially increasing and the oscillations in the super-horizon scale. Yeah, except for the divergence near the horizon. So next, I'm going to talk about the non-slow limit case. This is the plot is the numerical result for the non-slow limit. We chose this parameter V0, M, and delta to satisfy the non-slow limit case. The black dashed curve is the steepest descent, which is predicted to give the most dominant probability in the analytic solution Hartle-Hawking wave function. So note that as alpha increases, the curve goes to the top, I mean the point where the potential local minimum, yeah, the curve, I mean very exponentially increasing. Okay, so this is the same plot. I mean, this is just some pi slices of this plot. And the blue curve is for when pi equal minus delta, and the yellow curve is for pi equal minus 0.5 delta, and the green curve is when pi equals 0. So first, you see that for large alpha, the local minimum curve, I mean the curve at the local minimum potential, actually the blue curve is exponentially steeper than the local curve in the local maximum point, I mean the green curve. But yeah, it is not interesting. But however, let's see the yellow curve. The probability start becoming larger than the first steepest descent as alpha increase. So the first steepest descent means that the first peak and the the first steepest descent means this from this peak, Yeah, but you see that there's a sudden jump, and even in this region, the probability is more larger than the steepest descent. This is unexpected phenomena in the analytic result. Yeah, this is plot when we change the potential parameter V0. This is for 0.02. This is for 0.01. This is for 0.005. So we see that if the slow roll condition is violated more, this is the violating direction, the unexpected phenomena is getting clear. You see there's some bump, the bump is more clear. Okay, so we try to interpret this unexpected phenomena. So let's see the plot. Okay, first the blue curve is just the yellow curve, the same curve. And the thick blue curve means the analytic result, I mean, from the Hartle-Hawking wave function. So first, see that the two curves overlap and match well when alpha is smaller than 1. But for when alpha is larger than 1, there appear sudden jumps in the right blue curve. Yeah, it seems, I mean, the numerical result seems like a sudden jump in the potential work problem in quantum mechanics. Seemingly, it seems that there is no special reason to, the sudden jump appear there. However, we should also consider the dynamics of pi. And this is actually not a one-dimension problem, so we should think about another direction, pi. So therefore, we guess that the interference of the pi direction oscillation comes with shifty oscillation. Okay. So following our interpretations, we can divide this plot as 3 parts. First, this is a non-classical region. So the wave function increases exponentially. And this is oscillatory region. So this region is classical. And this blue region, this green region, the oscillation of A is dominant, and in the yellow region, it seems that the pi direction oscillation seems more dominant. Okay, so now we have two overall interpretation in this situation. So first interpretation is that we neglect this unexpected region, yellow region, and only the steepest descent region of the quantum domain decide the probability, which means that we neglect this yellow region and just follow the analytic solution, the black curve. Yeah. But the advantage of this interpretation is that, okay, this is consistent with the Euclidean analytic calculations. But this neglects the highest part of the probability in the probability distribution. So the second interpretation is that we don't neglect this yellow region and just respect this yellow region. But in this case, the problem is the probability distribution prefers to the superhorizon scale size universe. Yeah, so this region, this region, so the universe we are gonna find is the size is larger than the Hubble scale size, yeah, which is also some property. Okay, so conclusion. In this paper, we investigate the Hartle-Hawking wave function by numerically solving the Philadelphia equations. In the slower limit, the result has turned to be very consistent with the energy approximations. On the other hand, for non-slower type potentials, we observe that some unexpected phenomena appears. Our interpretation is that in the classical domain, due to the interference between the A and pi, the overall amplitude becomes larger than that of our original extent analytic solution. Okay, so thank you.
Thank you. Is there any questions? So here you employ the Hartle-Hawking wave functions.
Yeah, right. As an initial condition.
Yes. Then what is the good things? What is the good result if you once you employ the Hartle-Hawking wave functions rather than other boundary conditions?
So I mean, this project is for Hawking Hartle wave function describe the no boundary universe scenario, which is a very famous scenario by Hawking. So we try to compare that popular known analytic result, but we calculated it numerically, and we saw something unexpected things. So just our aim is just compare this Hartle-Hawking's proposal and its numerical version.
Okay, thank you. Okay.